honored and humbled to give the first presentation this afternoon because I'm totally out of the field of mathematics. And I was very happy to receive the invitation because I'm really interested in big data research. But after I was aware that this is a party for mathematicians, then I really got nervous. I got even nervous after I know that my presentation have 45 minutes, which is really unusual in my field. Okay, but I'm happy to share my research with mathematicians and data scientists. But please be nice to me because I don't have very good mathematics background. I'm Zheng from the Southern University of Science and Technology. This is a very young university in Shenzhen. Probably you learn about this university in recent days because of the disturbing gene editing things. Actually, the professor is giving talk in Hong Kong University today. So, yeah. So first, some background, because most of you may not be familiar with hydrology. So the background is the entire world is facing severe water issues, many challenges, water challenges. For example, water shortage, water pollution, flood risk, and many water-related ecological disasters, such as disappearing inland lake, like vegetation degradation and algae blooms. So these water issues actually are not far away from us. In the city I'm living in, Shenzhen, actually we have all these problems. For example, the subway stations are frequently flooded during big storms. And Shenzhen has several very highly polluted rivers like Maozhouhe. And also in the nearshore area, we have red tide due to algae blooms. And in Shenzhen, although we got a lot of rain, we have a lot of rain every year, but the water supply is mainly from outside of the city. For example, we have two water diversion projects. One is one was built like half century ago, which also provides water to Hong Kong. That's the old diversion project. And about early this century, we had another diversion project to supply water from Dongjiang to Shenzhen city. So even in wet areas, Shenzhen is still great short of water resources. So to address all these water issues, it's fundamental to understand the hydrological cycle of the Earth. So, okay, so let me spend a couple of minutes to explain the hydrological cycle. So as you may know, so the water can evaporate from ocean and from the land into the atmosphere. Then it can become cloud, and it can produce a precipitation in terms of snow or rainfall. So when the precipitation reaches land, it creates surface runoff, or it infiltrates into soil, all the way down to a saturated air zone we call the groundwater. And both the surface water and groundwater can flow from highland to lowland and eventually come back to the ocean. So that's a very short description of hydrological cycle. So hydrological cycle is actually coupled with energy cycles of the Earth. And also, it's the driving forces for the cycles of many other materials like carbon, nutrients. So basically, it's critical to the Earth. So the importance of hydrological cycle to the Earth is just like the importance of blood circulation to human. So we need to understand the hydrological cycle and also to quantitatively describe it. In 1969, so Fries and Harlan wrote a classic paper which provides a blueprint for physically based hydrological modeling. So actually, the current ongoing hydrological modeling is still following this blueprint. So this blueprint emphasizes the following things. First is the continuity between groundwater flow and unsaturated flow. And the second is coupling with surface water with groundwater. And the third is to emphasize the role of vegetation on the hydrological cycle. And the fourth is to consider the influence of meteorological phenomena. So I just want to emphasize, so the modeling mainly addressed two variables. The first is the runoff, that is the flow out of the watershed. So why this is important for the modeling? Because it's a measure of the available water resources to human being. And the second variable key to the modeling is the evapotranspiration, including evaporation and transpiration. Why this ET is important? Because it reflects the activity strength of the ecosystems on the Earth. So that these are two variables most concerned by hydrological modeling. So physically based modeling, so this figure just bring a column from the subsurface into the atmosphere. And as we can see from this figure, typical hydrological models actually address this portion, that is from the saturated zone, the zone saturated with water, the groundwater, the variably saturated soil zone, and the surface layer, which includes vegetation. So that's the zone that typical hydrological model address. And the typical hydrological model only consider water balance. From here above into the atmosphere, that's the job of climate model, which mainly consider energy balance. Okay. So now our society is developing the new generation of hydrological models, which include the atmospheric boundary layers into the modeling frame. So this range is what the new generation of models concern about. Okay. So this reflects the idea to model modeling from the subsurface into the atmosphere. So by considering both water and energy balances. So I apologize that this slide is the only slide that have differential equations in my presentation. So, but I won't explain all these differential equations. So these just give you some concept of what kind of hydrological model I'm talking about. Okay. So, although the physically based model is still under development following the blueprint, it has been widely used in water resources management, for example, to support hydropower production decisions, to support agricultural development decisions, for soil and water conservation, flood control, water quality protection, and watershed restoration, just mention a few. So the physically based models have already been widely used. So let's look at the other side, data. So in our community, we are talking about big Earth data. So this year, the new Chinese journal titled "Big Earth Data" is coming to it's just being brought up. What big Earth data? Because we have all sorts of sensors, devices to observe the status of Earth from many different aspects, from the ground level into the space level. For example, we have far space satellites and near space satellites. We have airborne sensors on different platforms like aircraft, weather balloon, helicopter, drone. Also, at the ground, we have all sorts of radar to measure different variables of the Earth. Also, we have very traditional or classic ground-level instruments like meteorology stations. We have solar radiation observation devices and other measurements. Okay, so we have all sorts of data related to the Earth. That's we call big Earth data. So big Earth data, arguably big data, because I know in other fields people have different definitions about big data. So someone don't think the data I mentioned are really big data. So I say it's arguably big data. For example, it has at least the three features: the variety, because all those sensors collect multi-source data, and some data are in plain text, some data in point data. Also, we have polyline, polygon data, raster data. So multi-source with a significant variety. Also, the large volume. So we know the data need to reach a PB level, so we can call it big data. So with all these satellite data, actually the big Earth data reaching that level. Okay. Also, velocity. We have some high frequency measurements in our area, like we can have real-time water level monitoring, and we have high frequency measurement of meteorology variables. Of course, the GPS data is the most typical data with high velocity, because anytime we are receiving a lot of GPS data. Okay. And also, like in area of water quality monitoring, so we have on-stream monitoring system, like give you a very high frequency measurement of the water quality. So arguably, we have a high velocity of the data transfer from all sorts of sensors. Okay. So for hydrology, so the big data mainly from satellites. For example, this picture shows NASA's water cycle mission. So it launched many satellites carry different kind of sensors. So different sensors can measure different aspects of the hydrological cycle. For example, this like GRACE is the most well-known satellite to provide water information. So it measures the column water content of the Earth. And if it observes some change of the water storage, it mainly reflects the change of the water stored in soil and the groundwater. Okay. Also, TRIM and GPM are the most used satellite data for global precipitation estimation. Okay. So this table also give you a list of all the main satellites that provide the measurements of major hydrological variables. Not only for hydrological variable, some satellite can also provide land use information, vegetation information. So the most common data source is MODIS and the Landsat. You may heard about that. So that's the big data, major sources of big data for hydrology. Let's talk about date-driven modeling, because it's quite common in other fields. And in our field, the date-driven modeling has also been practiced using machine learning techniques has also been practiced for a while, for nearly 2 decades already. So in our field, the most frequently used approach is just ANN, the classic ANN, artificial neural network, and also like a supported vector machine SVM or genetic programming. Yeah, we have many applications of them. And the most classic problems addressed by date-driven modeling is the rainfall runoff modeling. That's if we know how much precipitation, we would like to know how much would the flow be. So that would be important for water supply and flood control. Okay, so yeah, although there are many applications of date-driven models, so it's still not considered the mainstream in the hydrological modeling by our society. So the main problem is also the applications are mainly ad hoc applications. It's very difficult to generalize these date-driven modeling studies. Okay, so this is the background. Then I will move to 3 study cases my group has done. Okay, so before going to the cases, I would like to say something about the challenges here. So I put data model applications, the chain here, and for each node of the chain, I would like to discuss the challenges. So for data, so in our society, it's really big in the air, but small at the ground, which means the big data really mainly from the satellite data. But at the ground, we really lack of high frequency, large volume observational data. And the second one is we are still lack of direct measurements because the radar or the satellites, they provide indirect measurements. You still need to calibrate their data against some ground level measurements. But the groundwater measurements are still very limited because those devices are expensive, and also those devices only provide you point measurements, not aerial measurements. So that's 2 big challenges. For the model, on one side, the physically based models involve significant uncertainty. So in past 10 years, most of my work addressed the modeling uncertainties of physically based model. I think that's why I was invited, because I published a series of papers about modeling uncertainty. So the uncertainty actually came from the data gap and the model structure. So on the other side, the date-driven models have higher accuracy in many cases. So that's proved by many applications. So date-driven model can provide you better predictions, especially those short-term predictions. But the problem is that they have very low transferability. It works for one area, but it doesn't work for another. At the application level, one problem I would like to point out is that physically based model can offer deep insights, but they are very computationally expensive. Okay, so although we have supercomputer to run the model, but in real world daily regular management, it makes no sense to use supercomputer to support the daily decision. Okay. On the other side, date-driven models are cheap to run. Once they are built, it's very cheap to run. But they can only produce case-dependent results. So for one application, this model works good, but maybe very bad for another application. Okay. So challenges means research opportunities. So I put 3 key questions here. So at the data level, I think a question is what kind of roles could opportunistic sensing and crowdsourcing play in hydrological modeling? At the model level, we need to answer this question. What kind of roles could big Earth data and deep learning play in hydrological modeling? And at the application level, we need to consider how to merge the strengths of both physically based and data-driven model. So in the recent 2 or 3 years, my research interest shift from modeling uncertainty into these questions. So our group are doing some research, but very preliminary. So next I will just present some preliminary research results to you, and hopefully can get some feedbacks from you. So the first case is we do a camera-based rain gauge, so rain measurement. Okay, so this figure shows you the existing measures to get rain data. So first is satellite, as I said, satellite. So satellite is based on radiation signals, and it provides aerial data at the scale of this much, like hundreds of kilometers. Okay, and the next one is radar. Radar is also gets data from the remote. Okay, but radars depend on reflexivity. It provides also aerial estimate of the precipitation, and its spatial scale is about several to tens of kilometers. Okay. So more traditional measurement gauge is a rain gauge like this. It's just count how much water can be collected by the vessel. Okay. And this one is more advanced point measurement. It's a disdrometer. It's just count the size distribution and the number of the raindrops. Okay, so these are, I would say, direct measurements. And the radar and the satellite are both indirect measurements. So these these represent the most often used technologies to get rainfall data. But as you can see, so for these methods, some are just low resolution, some are just very high cost, some are just indirect. So eventually we are still looking for a high resolution, low cost, ground level precipitation monitoring network. So we need such a network to really get some big data at the ground level. So in this study, our idea is we just think about this question. So can existing closed circuit televisions, as CCTV, surveillance cameras be used for opportunistic sensing? So we know there are many this kind of cameras, many everywhere. So yeah, except private space. So, but can we use that to measure rainfall? Okay, that's an interesting question. Yeah. So start from this question, we develop a new approach to measure. We tried to measure the rainfall intensity in real-world conditions based on videos acquired by ordinary surveillance cameras, which means cheap cameras, not professional level cameras. Okay. And in real-world conditions, because a few studies attempt this kind of things, but they just use very hypothesized background to do the interpretation. But we want to check if we can do that in a real-world environment and use very cheap device. Okay, so this the figure on the right shows the basic framework of our approach. So in short, it can be consists of two parts. One is the algorithm to identify rain streaks from the rain-free background. So separate rain streaks from the rain-free background. That's the first part of the algorithm. And the second part of the algorithm is to, based on the identified rain streaks, we estimate the rainfall intensity to get the quantitative results about the rainfall intensity. Okay? So this slide shows you the basic idea of the first part of algorithm. That's the rain streak identification. So in pattern recognition, so in computer vision area, so there are many research tell you how to identify specific items from a picture. But it's not straightforward to separate rain streaks from a complex image. Previous methods mainly do the separation mainly based on the difference between consecutive frameworks. That's the algorithm. The previous algorithm look at what's the difference between two consecutive frames. Based on the difference, then it tried to separate the rain streaks. But in our approach, besides this difference, we also the new approach also look at the visual properties of each frame. So it considers more factors to separate the rain streaks. So in short, so the original image O can be decomposed into the background image B and the rain streak layer R. Okay, so this picture shows you the original one, the background one, and the separated rain streaks. Okay, So these three, is the first column and the third and fourth column just tell you some the visual properties of different layers in this frame. Okay? So our idea is to come up with this convex optimization problems. So the objective function actually consists of 4 items. Let's look at the last item first. The last item is actually to see it's actually what I mentioned here. So that's the difference between consecutive frameworks. So it represents the temporal stability of B, of the background information, which means we want the separated background layer as stable as it can, because it's a minimization problem. And there was 3 additional items. The first one is actually the sparsity of the rain streak layer. Okay, that's an L1 norm of this matrix. Yeah, so the idea is that we know, like this image shows, the rain streaks are sparsely distributed in the space. So we want to see it's, we assume the rain streak should, this sparsity should be, we should see sparsities from this layer. And the second and the third items actually reflect the vertical total variation. That's the yellow lines indicate. Along the yellow line, the vertical one, of the rainfall of the rainfall layer. And the third one reflects the horizontal total variation. The red lines indicates in B, in this layer, in background layer. Okay. So this is just the idea is that like in the rain streak layers, we want the vertically we prefer to see more zero values along the zero difference along the line, along the vertical line. Sorry, along the vertical line, because the rain streaks are lines, vertical lines. If there's no significant wind impact, the rain streak should be vertical lines. So we would be happy to see small vertical variations in this image, the grayscale value, small variation of grayscale values. Okay, so this is just another one to measure the horizontal change of the grayscale value in the background information. So we did not grab this object function from the air. So we actually made a lot of tests, and eventually we think these 4 items are relevant. So to solve this convex optimization model, we use a wider use approach, alternating direction method of multipliers, ADMM, to solve this huge convex optimization problem. Okay. So we performed the comprehensive test to see the parameter sensitivity of the rain streak identification algorithm, and to come up with some general rules to optimize the parameter choices. And we checked the convergence speed, and also we evaluated the impact of wind. So just very give you some idea of what we have done to test the approach. Okay, so the second part of the algorithm is to estimate the quantitatively derived the rainfall intensity from the identified rain streak layer. So this algorithm is actually based on classic geometric optics and microphysical characteristics of the raindrops. I will skip all the details of this algorithm because it's quite classic. Okay? So our major innovation, novelty is in the first part of the algorithm. So let's see the real-world application of our technology. So On our campus, we install an ordinary surveillance camera. This one, it's just here. And it can change the angles, so it can shoot 3 different scenarios. So we just check. So our method is robust for different scenes, okay? And in this summer, we recorded 5 rainfall events with varying intensities, and it's more than 6 hours. It's about 6 hours long video, okay? And we set the camera to take just 1 frame per second. It's a slow rate. Also, we have this one. This is automated weather station. We need to calibrate and validate our algorithm. So we need direct measurements of the rainfall. So we also have a rainfall station. Okay. So this rainfall station measures the instantaneous rainfall intensity every 30 seconds. Every 30 seconds. Oh, sorry. Every 50 minutes. But our calculation, based on our computer vision, our calculation is 30 seconds. Every circle is 30 seconds, but this measures every 15 minutes. The cumulative rainfall in every 15 minutes. Okay. So this video just give you an idea of what this method can do. So the video on the left tells you the original video of the rainfall. And on the right, the video after identification. As you can see, the red dots or red shapes represent the rain streaks identified by our algorithm. So with this technique, we can this is the rainfall intensity derived from the video. So it basically tells you once we set the camera there, and we can give you real-time data about the rainfall intensity. Okay. So how good is the result? So these 5 figures tell you the validation results. So the red dots represent the accumulated rainfall volume measured every 15 minutes by the rainfall station. And the blue line tells the trajectory of our estimation. Okay, so we just compare the blue line with the red dots. As we can see, our algorithm generated very good results. Okay, but in certain cases, like this one, so this is a really huge storm. When the storm is very huge, so it's just blurred. The images are blurred, and then the performance of the algorithm is not that good. So it means we still need to improve it to deal with very huge storms. Okay. Before our approach, we only see 2 studies similar to our idea. So we compare our research results with previous approach. So we can see the main merits of our approach is that we very cheap. We only $100, but they use professional level cameras, and we consider real world backgrounds. They consider very simple backgrounds, and our accuracy is also good. Better than previous study. So in summary, so low cost, more realistic scenes, and higher estimate accuracy of our approach. And this study shows the great potential of using existing CCTV networks for the opportunistic hydrological sensing. Okay. So let me talk about the case 2, the flow modeling using computer vision. Okay. So in this study, the idea is to use computer vision to prepare model inputs for data-driven models, which represents a new framework to assimilate big Earth data into data-driven hydrological model. So we use a watershed on the northern margin of the Qinghai-Tibet Plateau as the study case. And in this modeling case, we consider precipitation, temperature, leaf area index as the model input, and the stream flow as model output. So what's the problem with traditional strategies? The problem is they cannot sufficiently account for the spatial heterogeneity of data fields. For example, in some cases, people just use some data at selected points as the model inputs. Then the spatial information is not fully exploited. In other cases, they just average over entire watershed. Then just no spatial information is exploited at all. Someone tried to average over individual subbasins, like they separate a big watershed into like tens of subbasins and average data on the subbasin scales. But still, spatial information is not fully exploited. A straightforward method to account for the spatial heterogeneity is just to use data information at every spatial unit, like every grid cell. So that's the most straightforward one. But if we do this, then we will encounter the curse of dimensionality, the huge dimension of the input data. So we want to avoid this, and we also want to make better use of the input data. So the key idea is to use the computer vision techniques to transform a data field into an one-dimensional feature vector. Then the feature vector can be input into the DateDriven model. So in our study case, we consider two categories of feature. One is the intensity of the image. The other is the texture of the image. So this figure gives you the basic idea. So we have images or videos. And we use computer vision technology to extract these two features using certain algorithms. And we make a long one-dimensional feature vector to create such a feature vector. With this feature vector, then we can do the modeling very easily. So here we see the first row shows you the input data fields as videos. So the precipitation, temperature, and the leaf area index are all changing. Then our algorithm can extract and can transfer all these videos into one-dimensional feature vector, which is also dynamic. As you can see, the color is changing. Okay. Then this feature vector is input into an artificial neural network model and makes the prediction, as this figure shows. Okay. So this video just tells you the whole process of how to use the computer vision-based approach to do the data-driven model, which is quite different from the traditional way in our community. So the prediction is well matches the observation. Okay. So we compare our approach with the more traditional ways to prepare the input data. So as we can see, so the x direction shows the lead time, is the prediction length, is how many days you want to predict beforeward. Okay, so as we can see, so when the prediction length increase, the performance, the y-axis indicates the performance. So the performance decay is quite slow. But the other approach has a very significant performance decay. So our approach is very robust. Okay, and for long-term simulation, we compare our model with existing process-based model or physically based model. So this column shows the model performance. So the conclusion is that the CV model is much easier to build. It's very easy to build, but achieves a comparable or even better performance than those existing process-based model. Okay? So also we check the capability of transfer learning for ungauged basins. So we can see our approach works better, and also we argue that the framework we proposed gives us the flexibility to fuse multiple source data and assess the roles of different predictors. So the last case I will go over it very briefly. So is about the surrogate-based optimization. Because the physical-based models are very expensive, so it's very difficult to directly use them in analysis, which requires numerous model evaluations, such as optimization analysis, uncertainty analysis, etc. And strategy is just to do surrogate modeling or called meta modeling. So surrogate model can replace the original model fully or partially in the analysis. It's more cheaper, and it's usually in the form of the response surface. That's where the machine learning can come in. So machine learning can be a good approach to come up with some response surface. So we build a model for a watershed in the western part of China, which is about more than 9,000 square kilometers large. So in this area, there are intensive agriculture and irrigations compete with the ecosystem for precious water resources. We have built a very complicated physically based model. And we developed an algorithm. So in this algorithm to optimize something by incorporating the physically based model. So if we use the original model, then it would be very computationally expensive. But this algorithm, in this algorithm, we coupled the support vector machine with a heuristic search approach. So basically, the basic idea is in the search, we don't have to use the original model every time. We only need to use the original model hundreds of times. Then we can finish the whole set of optimization. And for example, we use like 200 initial examples to start with, and the optimization can converge with within less than 300 examples. Okay? So the surrogate model based on SVM can adequately replace the original model in many aspects. So this figure just tells you it can do good job for many different hydrological variables. So it just shows you that in this case, the strengths of physically based and date-driven models are merged here. Okay? So we perform a number of optimization schemes considering different hydrological conditions, management concerns, and constraints. The main point here is if we want to do all these optimizations, use the original model, even on computer clusters, we need years to finish that. But with this surrogate-based model, to use the machine learning to replace the original model, so we can reduce the cost from years to days. Okay? And here just an example of the optimizing results. So it's tell you where to pump more groundwater and where to pump less groundwater. So in summary, so this study presents a good case in which the strengths of both physically model and date-driven models are nicely merged in a real-world application. Okay? So finally, some concluding remarks. So the first two are my feelings about these 2 or 3 years research on big data and machine learning. So I'm aware that the recent progress of big data and AI opened a new door for the hydrological community, which has been relatively conservative in the past. So to be honest, our community is very conservative. And then I know hydrologists have much to learn from data scientists. That's why I'm still here, although I'm nervous because I'm really out of this community. The next 3 points is, first, opportunistic sensing can help resolve the problem of small at the ground, like the camera-based rain gauge I have showed to you, and definitely deserves further studies. Then computer vision can bridge the gap between big Earth data and hydrological modeling, as I showed in the second study case. And as I showed in the last study case, physically based model and date-driven model actually should be friends. They are not enemies, and they can co-evolve. Because in hydrological community, actually there's debate. Someone think that date-driven model using deep learning may replace the physical-based model, but others think way to go. But I think they are not enemies. They should make friends and co-evolve. So eventually, 2 questions. First, the existing data are still not big enough to support the deep learning. So actually, my group have tried different cases to use deep learning for hydrological modeling, but we have not achieved good results. So I didn't present that. So not big enough for deep learning for classic hydrological modeling. And the last question is how to make use of big data from other domains like the internet or sorts of socio-economic big data is still a big question. So more research are expected. So finally, thank you for your attention. And that's all for my presentation. Thank you.
Questions? Okay, so I have a question.
No.
Here's a question.
Okay, go ahead.
So I appreciate you mentioned about the transferability regarding the data-driven modeling. I think this is a general question for not only in hydrology modeling, but also in many multi-physics modeling. So in your second case, you talk about using the machine learning concept to build a model. So can you talk about the transferability issues in this case?
Okay,
In general?
Yeah, thank you for the question. So in that case, what we have done is like we calibrate the model in a part of the area, and we use that model in another part of the area to see if it works. So it works in our case because these two parts are still not far away from each other. So they still share some common features. I'm not sure if I pick another faraway watershed it works good. I'm not sure. But I think it was not that good in that case. Yeah, so that the transfer learning I have done in this study case is still very rudimental. So two areas not far away from each other. I think basically just not big enough. So that if we have global data sets, so we may make a general data-driven model for at the global level. So it's a way to go, I think. Okay.
Thank you. Any other questions?
Can you go on the previous slide? I have mostly commentary, not questions, but I like some of these bullets. And so you say physically based models and data-driven models should be friends. So in many ways, it's not one or the other actually.
Yes.
Both really need to be together. In some sense, if the physical models are not, good enough to capture the reality, your observations compensate for that. So you have to use both of them together. If the models are very good, there is a possibility, and this is work that's happening these days, that the number of observations that you will need are extremely few, and the concept of big data and the concerns that you said in your current report, may not actually exist at all. In other ways, you may be able to go away with very limited, possibly zero data. And we'll talk a little bit about that tomorrow, actually with some applications to hydrological applications. I think I look at item F, this concern about big data in general, you can address it in a Bayesian setting. And so that way to capture the epistemic uncertainty coming from limited data. And so you can say how much information you are lacking and that captures uncertainty bounds basically in your predictions.
Okay, thank you. Yeah.
If there's no questions, I expect to see you again.
Thank you.